שעברה, אז בואו נזכיר, אז יש לנו x קומפלקס סימפליציאלי, ואנחנו הסתכלנו על האופרטור הכוספה מ-CI x f2 ל-CI פלוס 1 x f2, כן, שמוגדר באופן הבא, דלטה I של f, כן, פורמלית אנחנו, זה קוצ'יין, זה פונקציות f ו-ci, שזה פונקציות מ-xi, זה מוגדר על ה-i סל, אז דלטה I של f של טאו, כאשר טאו זה ב-xi ועוד אחד, נכון, אני צריך לקבל פונקציה שפועלת, just in English. We looked last time that x is a simplicial complex, and we have a map, delta I, the co-boundary map from Ci to Ci plus 1. Ci is the functions from xi, from the I cells to f2, and then delta I of f of tau, where tau is the I plus 1 cell, is simply sigma. We don't need, because we work over f2, we don't have to worry about orientation. So this is sigma of f of sigma, where sigma is a subset of tau, and sigma is of codimension 1, namely this is an I cell. And now, if pi are the co-boundaries, the image of delta I minus 1, I'm kind of working with all the i's together, then we define definition, the expansion was epsilon I of x is the minimum over all, the minimum of delta I of f norm. I will remind you in a minute what does it mean. Delta I norm divided by the norm of the coset of f, where f runs over all the cochain in Ci minus pi. Well, I admitted that this looks like a very non-intuitive definition, but I showed you last time that if you look at epsilon 0, then we are getting the Chigger constant. And so there is maybe some justification to call it expansion. And today I will show you another aspect in a completely different direction, which will show you that in some sense it has other properties which are related to expansion. So now let's recall what is a norm. The norm was defined like that. I want to be a little bit careful here. Though you can define different norms. You see, one can define the norm in several different ways, but and then the expansion is always with respect to that norm. The way we will work here, that we define if sigma is in xi, then C of sigma is the number of tau in xd. T is the top dimension. So maybe I should say at the beginning that x is a pure, let's say, pure simplicial complex. Namely, pure means, I don't know why they call it pure, but pure means that the maximal simplices are all of the same dimension. Pure simplicial complex of dimension E. We always involved with things like that. And the C of sigma is the number of tau in XD such that which contains sigma, and the weight, we know this is just a question now of normalization. The weight of sigma is C of sigma divided by D plus 1 over I plus 1 divided by XD, by the size of XD. Now, and the important property, that this is like a measure on xi, namely sigma, the sum of sigma in xi of W sigma is 1. Now, one can argue what is the natural measure to take. You know, some people like to take the measure simply. If you really want, let's say that we want this property that would be convenient, you can always just take to give everyone 1 over xi. And it's anyway equal to 1 over xi if we are in something which is very regular, namely if all the C sigma are equal to each other, if all the C sigma are equal to each other, namely if for every I cell the number of D cells containing it is the same, then you don't have to compute it because you know that all of them have the same weight and the total weight is 1, and therefore the weight must be 1 over xi. So this we checked last time, and this is easy. And the norm now, if f, I actually for some reason like to call it alpha. If alpha is in Ci, then the norm of alpha is simply the sum of weight of sigma, where sigma is in alpha. What does it mean, sigma in alpha? Alpha is a cochain, right? It's a functions on I cells, but I can think of it as a subset of I cells. I can think of it, the function is just function which get values 0 and 1, so I can think of it as a characteristic function of some set. So it will be convenient to identify and to think about such an alpha as a subset of cells. And now what is the coset of alpha? The coset of alpha is simply alpha plus bi, and the norm of a coset is the minimum norm within that coset. Namely, it's the minimum among all, the minimum of the norm among vectors of the type alpha plus delta I minus 1 of smaller cochain. Okay? So, it takes time to digest this definition. I showed you last time that I computed it I want to recall that I computed it for 1, and we saw that this is kind of a normalized Chigger. And we also add one example theorem. We will put it only in dimension 2, so let's compute dimension 2. If x is delta n2, so this is the complete two-dimensional complex on n vertices, then we saw that epsilon 1, this is, so epsilon 0 is basically the Chigger constant for the complete graph, which is trivial to compute. But this was less trivial, but we saw that this is greater or equal to 1. It's slightly more than 1. It's 1 plus little o of 1. So it was like, I think it was something like n over n minus 1 or n minus 2 or something. Anyway, it's greater or equal to 1. That's the important thing for us. And today I'll make some simplification. You see, I'm doing this little results will give us some application. This is linear Shulam and Gromov kind of independently. Okay, so now I want today to relate this to a completely different area, something which is called in computer science property testing. Now, what is a property testing? Property testing is the following result. Is the following topic. I'll make a definition which will be. It's a special case you can talk about or something which is called, let's say, Q epsilon testability. And let me make the formal definition and then we'll try to explain what does it mean. Let A be a finite set, Wn a subset of A to the n. Just take all the n, the n tuples. Maybe I'll do it a little bit slightly more restricted situation, which would be enough for us. So let Pn be a subset of An. We say that the membership of alpha in Pn is Q epsilon testable if there exists okay, usually we say that it's testable if there exists Q and epsilon, maybe should I say, is testable, maybe I should say that it's testable if there exists epsilon greater than 0 and some integer, maybe Q is not a good number for us. Well, anyway, I'll use it for some reason, they use it always Q. There exists epsilon Q, say an integer, and a randomized algorithm. You will see that it must be a randomized algorithm somehow. Randomized algorithm. What should I call the algorithm? Let's see if I gave it a name. Well, I'll just call tester. There is a tester such that the tester reads only Q bits of alpha and answers yes if indeed alpha in Pn. The tester wants to check if alpha is in Pn or not. But is allowed to read only Q bits. So Q is independent of N.
Q bits or Q entries? Because A is not 0, 1.
Yeah, okay. Yeah, Q entries. Maybe it will be 0, 1. But it must answer yes, for sure, if it is inside. So never making mistakes. And it answers no with probability at least epsilon time the distance normalized between alpha and Pn if alpha is not in Pn. Okay, let me explain. You allow to read only a bounded number of bits, qubits, and you answer yes, and you do some calculation with these bits, you answer yes. If alpha is in Pn, then the answer, we don't allow any mistake, the answer. If the alpha is not, then maybe you have a mistake, of course. You can see that must be the case. But if alpha is really far from Pn, then there is a large probability that you will detect it by this random algorithm. Okay. Now, what is the distance? Distance means the normalized distance. Okay, so now usually the way they do it is simply by the Hamming distance, namely in how many entries they are different than each other, divided by n. Right? This is a probability, then this should be number between 0 to 1. You take the distance in how many bits. You take the closest element in Pn to alpha, you divide it by n, and you get the normalized distance. But we can take if our metric is different, we can use a different metric. For example, for us, it would be better to use this metric, but anyway, in the case I'm going to illustrate it, it's going to be anyway the standard normalized metric, metric. So you can play the game in various, whatever the context is convenient. Let me give you just without proof, but just the classical theorem which started all this. I forgot that they always call it PLR, I think. So I forgot to prove it. Rubinstein. So the PLR theorem says that linearity is testable. So linearity is testable, which means you take the vector space, let V equal F2 to the M, and then let's look at the space of all, let A so A, you think of it as all functions, you take all functions from V to F2. This can be identified with F2 to the 2 to the M. So N will be 2 to the M. I took it all possible functions from the, sorry, not from A, from V. So for me, A now is F2, and N is 2 to the M. You put some order on the element, doesn't matter. So I look at all functions, possible function, see, don't confuse it between M and N. I look at all functions from V to F2, all functions, so not linear, all functions. So there are 2 to the M like that. Right? So this is a vector space of dimension 2 to the M. And the linear ones, and Pn, so this will be A to the N. And Pn will be all the functions from V to F2, so that F is linear. Okay? So, are you with me? So, and we want to detect, can we detect, we look at the function, and we want to know whether this is a linear function or not. Now, of course, if you really want to check linear, then you have to check on all vectors. And we know what we have to check, right? We have to pick up two vectors here, every two vectors, and to check if the function on their sum is, if whether f of x plus y is equal to f of x plus f of y. We all know what linearity means. The fairly amazing theorem here is that that the algorithm checking random x, y in V and answering yes if fx plus fy equal fx plus y and no otherwise is 3, and I think the best, maybe that was not the original result, but maybe it was improved after that, but it was improved that this is 3 2/9 tested. Namely, we check only 3 bits. We check only 3 bits out of the because, you see, I'm picking up random vector. Okay, the vectors are long, that's okay, but that's not what I check. I check my function. The function, somebody give me a list of 2 to the m bits, and I should tell you corresponding to, I know the order of the vectors and I know where they go. And now, but I am allowed to read only 3 bits out of it, and then I want to decide whether this is linear or not. This stupid little test is a great test. It's 3, it reads only 3 bits, and the probability of rejection is 2 to the 9 over the distance. Now let's understand what does it mean. It means that, let's say that you want to check if something is a linear test, and you want to check it with probability 99.99%. Okay? Okay, let's be careful. You want to check okay, let's the precise statement should be made a little bit more careful. Okay, we are getting 2 to the m vector. I can take a linear function and I can change it with 1 bit. Then of course it will be very difficult for any random algorithm to detect that this function is not linear, because whatever we check, the probability that it will touch that specific one is very small. And now we are talking about n going to infinity, right? That n is very large. But in some sense we don't care. Here the story is that this function for us is so close to linear that we don't care. Okay? We want to make sure that if the function is really is different than linear function by at least, say, 5%, okay, then I will reject it, then I will not accept it. Then you can decide what fixed percent what is your standard. Let's say you tell me you want that it's not more that the number of how you say, the number of bits in which it's different than linear, it's not more than 1%. Okay, so which means that the distance is 1/100, right? The normalized distance is 1/100. Every test, the rejection of the probability of rejection of every test is 29 times 1/100, right? But if I do, I don't know, 50 tests, how much I need in order to get from 1,000 tests. If I do 1,000 tests, then I will get the probability of rejection now is more than 99%, and this 1,000 is independent of n. That's the big deal. Okay? The 1000 is independent of n. It doesn't matter if n is trillion, 1000 test, namely reading only 3000 bits, can give you will do the test. Now usually, this property testing area got a lot of public relation. When computer scientists give talks about that, they talk about more general property, which not within linear spaces, and usually they declare like that: give me a proof of Riemann hypothesis. I will teach you how to write the proof in a formal language, and then if I want to check the proof, I will read only 3 bits, or only 30 bits from the proof, and I will tell you with high probability whether the proof is correct or not. Okay, so that's usually, this is a famous theorem called PCP theorem, which is, it sounds ridiculous because it's ridiculous in this formulation, but they love to give this formulation to impress us. I mean, all over the years, this impressed me, but when I started to study what it means, then I see that it really says something which is non-trivial. And this is a non-trivial theorem. I mean, it's not very difficult theorem, but like an hour, in an hour talk, one can give a proof of this theorem. Now, what I want to show you today, that expanders, high-dimensional expanders, give you tester for various properties, and there is actually very intimate relations between expanders and property testing. In fact, let me show you a baby case, which I have to admit that I never pay attention to that, even though I'm working with this expander for like, 30 years. And only then I saw that you can really characterize expanders using property testing. So let me start with the baby version. And this is the following. The following test. We take the set, what should we call it, y, the n, namely, what will be the name? 1, I look at the number 1 up to. And let's say that you have a function f from n to f2. And the question I will ask, is f constant? Completely trivial question in some sense. I have a function on the set, 1 up to n, and I want to check whether it's constant. Now, what will you do for that?
Pick 2 and compare them.
You will pick 2 and you compare them, right? And you can check what's the probability, and that's probably will be a test. But if you will do it just like that, you will see that this is not such a good test. The probability of well, it's a very good test. But I'll show you a better, not a better. I'll relate it to expander. So I will do the following. Assume X is an epsilon expander on N, on the set of vertices. On the set of vertices. Now what? And then the test will be the following. Pick edge E of X and check whether f of E plus is equal f of E minus. If the two sides coincide. If yes, answer yes, and if no, no. And the claim is, this is 2 epsilon. Now here epsilon expander is in the normalized sense. This is exactly, this is 2 epsilon tester. And in fact, this is 2 epsilon tester if and only if X is epsilon expander. This is a kind of an illustration of what we usually think about expander. We really usually think about expander as a kind of a random graph. And it's give you a way why this is better in some sense than the algorithm suggested by Shai, because the amount of randomness or the amount of random bits we need to this algorithm is smaller. In your algorithm, we need to pick up 2 numbers between 1 to n, right? When going to infinity, we have to pick up two random numbers. Here, we have to pick up 1 random number n and 1 random number between 1 to k. Say k is k regular expander, and k is constant. So we saved half of the random bits. Some people cares about things like that. Okay, so I'm not so excited about this application, but what I want to say that this shows that expansion is a form of property testing. It's a special case if you want to property testing. You can define one standard expansion using property testing. Now the question is, I think this is really just going over this proof, I believe you. And I really suggest if you really want to get into the subject, to do this as an exercise. It's nothing more than just going over the definition. And I will go and we'll do the more substantial case, showing you the general case. So that this will be a special case.
Here in the BLR, I don't know, maybe this is what you have in mind, but
what?
In the BLR theorem, if instead of looking at all x and y, you look at also you look only at pairs which come from an expander, then this
Okay,
works.
so I think, I was not sure what, I think it's true. I think it's possible. I think you can take, but you have to be careful. Yeah, I think it's possible here, just to take an expander on them. And I have the feeling that this is, I didn't check it carefully. I mean, one should really get into that.
Wait, suddenly you can start with a random subset, a random graph, then this will work.
Right.
But this is the cheating.
I think this will be okay, and I think this already been done, maybe by Avi, Wigderson, and some other, which they took an abelian group, even in a more general case, put a structure of expander on it. Now the question is if you want it to be a Cayley graph expander or just
any.
Just put any, you take any expander on the vectors, not necessarily
any expander on the vectors.
Right. Yeah, I think it should be. Yeah, I think it should give you something. I don't know. Maybe you pay a little price on the constant, but in principle, I think you can replace it by the. Yeah.
Because I don't see how the proof extends to any expander.
Yeah, no, I think. Now I don't remember, I have to say, but. I think I was thinking about that at the time, and then I learned that this was done. So it's a natural question that people ask. So now I don't remember if you can do it in any way, or if you do it if you make it into expander. Now, in principle, you can make a vector space f2 to the m into expander, but not using bounded number of generators, but using logarithmic number of generators.
If you don't care about if you consider it just as a set of points, you can put any expander you want.
Yeah, okay, if you put a complete graph, then
not
this
complete, no, but you can put any
Right.
constant degree expander, it will not have anything.
No, right. Yeah, but the question, if it has nothing to do with this, then now I'm not completely sure if
proof works.
if the proof works. No, I don't remember. I was talking about this thing at some point, but it's Italian, by Kidler, but I don't remember. I remember this. The answer is no. I don't remember what it is. Okay, so let me now tell you that the I-dimensional expander. What does it mean? So here is the claim that let's define the co-cycle tester. So in the following way. So X again, X D-dimensional pure simplicial complex, and alpha in CI of X2. The I cocycle tester to check if alpha is in BI. We want to check if alpha is in BI, whether alpha is a co-boundary. We are given a co-chain. Right, this is a vector, and we want to check if it is a co-boundary. And the tester will be pick randomly sigma in xi plus 1 with probability W of sigma. Remember, these weights we gave on the I plus 1 cells is a probability measure on the I plus 1 sigma. Maybe we'll call it tau. And if delta I of alpha of tau equals 0, answer yes, and otherwise no. And the very simple claim is theorem, but it's an easy theorem somehow. You know, once you really write it down carefully, then it's just going over the definition. If epsilon I of x equal epsilon I, oh no, why should I write it like that? I would say that this is n I plus 2 comma epsilon AR tester. Namely, I want to check if an element alpha in BI, sorry, I'm giving an element in CI, so I'm giving a co-chain.
So in this case, checking if it's in BI is precisely checking if it's in
constant, right? Remember, right? Exactly. This is a special case of that, because you remember that for graphs, you remember we computed it last time, and that was our explanation to the notion of that why this formal definition that we gave was really extending the definition of expander. We computed and we saw that B0, the zero co-boundaries are just two functions, the zero function and the all one function, namely the constant function. So this one is checking if a general co-chain, a general co-chain on graph is just any function on vertices, whether this is constant or not. The question whether it's constant or not is in this formal language is the question is whether this co-chain is a co-boundary. And so this is a generalization of this result. Now I'm giving a co-chain in CI, and I want to check if this is a, whether this is a co-boundary. And the claim is that this is, okay, so let's check. So let's prove it. If indeed this is a co-boundary, then every co-boundary is a co-cycle. Right? So if it is a co-cycle, then delta I of alpha is 0, and therefore delta I of alpha of tau will be 0, and therefore we will answer yes. So we 100% answering yes if this is a co-cycle. If this is a co-boundary, that's what. Now assume it's not a co-boundary. Now the only observation that you have to note this is the following one, and really think about the standard. Think about the standard normalization. You know that which is anyway. I erased the theorem which is important for today. So let's keep it. I think I can write this. Remember that the normalized distance is simply exactly what is the distance between alpha and bi. Distance normalized is exactly the number. Well, we can take with the weights, but let's assume that all the weights are the same, right? Assume that all the weights are the same. It's really 1 over the size of xi of the number of the number. So how should I write it? This is 1 over xi of the Hamming distance between alpha and bi. Right? But this is what is the Hamming distance between a vector alpha and a vector space? What? Covariant with it. This is 1 over xi of the minimum Hamming weight of gamma, where gamma is in the coset alpha plus bi, because right, this is a property of Hamming weight. What is the distance between alpha and bi? Let's say if the vector here, which is the closest to bi, is beta, what does it mean? It means that the Hamming weight of alpha minus beta is the smallest one. Is the smallest possible, right? Alpha minus beta or alpha plus beta is an element in the coset alpha plus beta I. This is clear? I mean, this is a trivial remark, but it should be. It should be really that when we define the expander as delta alpha divided by the norm of the coset of alpha, you can think of the norm of the coset of alpha. You can and you should think of it as the distance between alpha and the coboundaries. That's exactly the meaning of that. So this is basically the end of the proof, because what we are saying that, so what we get is that if the distance normalized of alpha and bi is is greater or equal epsilon I, right? This is the case because we have expansion. We have epsilon I expansion, right? No, what was it? Sorry. If this, I'm sorry. If this distance is equal to some number, I don't know, d of alpha, then what is the probability? Now, what's the probability that delta I of alpha on tau is equal 0 or equal non-zero, right? We want to see what's the probability that the tester will reject alpha, right? What's the probability? This is the probability that the tester is going to reject alpha. The tester will take the co-boundary of the co-boundary of alpha and will compute it on some co-cycle, right? On some I plus 1 cell. This probability is exactly the number of tau such that the number of tau such that delta I alpha of tau is not 0 divided by the total size of xi plus 1. Right?
So you're taking
Now, what is the name of this number?
You're taking tau with weight, no? Not uniformly.
What?
And your probability of choosing tau,
Yeah.
you're taking them by weights, your algorithm. Double the tau.
Yeah, and I assume that all the tau have the same weight.
Okay,
All the time, I'm taking the weight, yeah, I mean, I'm taking the weight as the normal, like, assume that I'm going to apply it to this case, and in this case, all of them have the same weight. I mean, I think it's so much better to, I mean, anyway, this is the most cases, and this is, I mean, please follow, because it's a trivial argument. There is nothing here than just going carefully over the definition. So again, what is the probability that my test will fail? I have an alpha which is not a co-boundary. What's the probability that I'm going to answer no? So my algorithm is we take alpha, we compute delta I of alpha on a random cell tau. What's the probability that I will fail? I know that delta I of alpha is not 0, so there are some taus for which it fails. Those are exactly these tau. The probability, and then the question is, what's the probability that I will pick up one of them? So this is the number of them divided by the total number, right? But what is this? This is exactly what we called before the norm of delta I of alpha. So the probability of failing is the probability of failing a test is exactly delta I of alpha. Now, that's always, that's independent of the structure of the, this is independent of the structure of the complex. Now, what we know in our complex, epsilon I x is by definition the minimum over all alpha in Ci minus Bi, right? This is now the case I'm treating. Co-change which are not co-boundaries, those where the algorithm is supposed to fail, is the minimum of delta I alpha norm divided by the norm of alpha. But what is this? We just expanded. This is the distance of alpha from Bi. Therefore, for every alpha not in Pi, delta I of alpha, which is probability of rejection, is at least epsilon Ix times the distance, because this is exactly the distance, the normalized distance between alpha and Bi. The normalized distance between alpha and Bi. Okay? So there is nothing here besides writing the definitions in this form. Here it seems like you're lucky. I'm going to take more than just the first. So because I wanted to show you, because in some sense it's so trivial. I haven't done anything besides just going carefully on the definition.
Yeah, this is just.
But after the break, I will show you some not so trivial applications. Applications which you will think of them, they are not completely apparent somehow, and they will be obtained very quickly from this observation plus the results of linear Meshula. Okay, so we do it after the break.